All right, so just a quick visual overview. I want to paint the picture of what this new chapter is going to look like. Chapter 8 is all about quadrilaterals, and we do want you to remember quadrilaterals are just four-sided shapes, and we're going to look at these specific four-sided shapes. And throughout this chapter, we are going to be studying properties of the four-sided shapes. And then remember, nothing in geometry can be assumed until it is proven. So if I say that this is a rectangle, we have to prove that it's got four right angles and opposite sides are congruent. And we're going to talk about very specific properties about all of these shapes. Okay? So hopefully you're familiar with all of these. You might not know the properties, but you hopefully know the shape itself. All right, so we're going to jump into our notes today, and we're going to start with section 8.1. If you want to label the topic as side lengths and angle measures of polygons. So we're going to look at just polygons in general, and then we're going to get more specific into four-sided polygons, which are quadrilaterals. All right, and then we're going to kind of look at how can we find missing sides and missing angles in polygons. That's our essential question. And this is section 8.1. You don't have to write the learning target. Note, I am encouraging you to use Cornell Notes, those of you that are familiar with it. It is a great way to study and be prepared for and review for geometry. Okay, so we're going to just kind of review angles really quick and then kind of explore and discover how do we find the total sum of angles inside of a shape. All right, don't write this. This is a real quick vocabulary moment. We've talked about interior angles with triangles. So I just want you to remember when we say interior angles, these are the angles that are inside of a polygon. So in this specific shape, here are my interior angles. And let's actually go to exterior angles really quick. Exterior angles form a linear pair with the adjacent interior angle. So if I extend one side, you see how the red lines are just extended? And notice how I kind of just go in one direction around the shape. If I do that, all of a sudden I have exterior angles, right? So those exterior angles actually form a linear pair, which we know these two, every blue-green pair that's connected have to add up to 180 degrees. And then we've got something called a diagonal. We're going to see this on the next slide, but a diagonal is a segment that joins two non-consecutive vertices. So all that means is if I take a vertice, that's a point where two edges meet, and I connect it. Now notice, see how this one's already connected? That's a side. If I connect it to the other vertice, that's a side. So what if I connect to the one that's not consecutive? So across from it, that's a diagonal, and that diagonal kind of splits this shape up into two familiar shapes. All right, so what we're going to do is we're going to take about a minute or two and have you guys write this down and then fill out the shape. Now, before you do that, I just want to give you a quick little hint. Here's our goal. What is the total sum of interior angles in a shape with blank number of sides? If you need to, drawing a picture may help. Here's an example. I'll show you how we did the quadrilateral. So let me explain this before you guys kind of cut loose. So let's look at a triangle. We just finished studying everything you could ever want to know about a triangle, right? It has three sides, name this triangle. There's one triangle in that shape, and the total amount of interior degrees for any triangle is 180. So what about if I have a quadrilateral? Well, what we want to do is we want to take the quadrilateral and split it up with a diagonal. So notice I've got a four-sided shape. I split that up, and now it creates two triangles, right? If I have two triangles, well, wait a minute. Triangle 1 has 180 degrees. Triangle 2 has 180 degrees. So that means the total sum of all the interior angles of this quadrilateral is 360. So what I'd like you to do is fill out the rest of this chart using the strategy that I used for the quadrilaterals. And we'll give you a couple minutes to get this done. Okay, so we just saw with a quadrilateral had four sides, and we were able to put in one diagonal and divide it up into triangles. And there's two triangles, and each triangle has 180 degrees. So one way to think of this is instead of writing 360 degrees, I could take the number of triangles, 2 times 180, and that would give me 360, right? So now let's look at a five-sided shape. Well, the name for a five-sided shape is a pentagon. And how many triangles make up a pentagon? Down here, I just kind of drew a quick one. If I create a diagonal and another diagonal, I split this up into 1, 2, 3 triangles. And then if I take that and I multiply it by 180, I end up with 540 total interior degrees. So if I was to add up all 5 of these angles, they'd give me 540. All right, now what about a six-sided shape? Well, six-sided shape is a hexagon, and it doesn't matter which point I pick, but if I draw the diagonal and I connect each non-connected vertice to the original one, I can see I've got 1, 2, 3, 4 triangles. Well, if there's 4 triangles and each one has 180 degrees, 4 times 180 is 720. Right? Now notice, we jumped here. Some students are like, ooh, I'm just adding 180, add 180, add 180. Well, I can't just add 180 here. The reason why is because I jumped. I went from 1, 1, 1, and now I went to 3. So you could find the pattern here. But if you started off with a 9-sided shape, which, by the way, a 9-sided shape is called a nonagon. And then if I draw this in, it's going to get kind of messy, right? Especially with my handwriting and drawing ability. So I could mark 1, 2, 3, 4, 5, 6, 7, but that kind of gets messy. Isn't there a pattern? We know there are 7 triangles, and 7 times 180, let me do that quick, that's 1,260 degrees. So what if I have an n-sided shape? Well, in this case, we call this an entagon, right? So polygon, notice how they all end in, almost all of them end in agon. So this is an entagon, meaning we don't know the number of sides, but do we know how many triangles there are? And that's my question. Did anybody figure out this, either this shape or this shape down here? How many triangles are we going to have in an n-sided shape? You know it. You can unmute yourself or throw it into the chat. Yes. Reagan said n minus 2. Why? How do we know that? Well, let's look at it. If n is the number of sides, if I have 3 sides, how many triangles did I have? I had 1. If I have 4 sides, there were 2 triangles. 5 had 3 triangles, 6 sides had 4, 9 sides had 7. So if I have n number of sides, there are n minus 2 number of triangles. Well, wait a minute. If there's n minus 2, can we come up with a formula for the total sum of the interior angles? Well, what do? I take the number of triangles and we just multiply it by 180. So we're not going to come up with an actual answer here, but we're going to come up with a formula. And that is actually our first theorem for today. And you can just basically see right there how it's generated. I think that's kind of a cool, nice little pattern piece for us to get to. Okay, if you didn't get this full chart, it will be posted on the notes when we get done with class. I'll post it up there. But let's generalize this and talk about our very first theorem. If I want to figure out the total sum of interior angles for any polygon with n number of sides, we do n minus 2 times 180. And remember where that n minus 2 came from. That was the number of triangles in that shape when we drew the diagonals, and then we times it by 180 because there's 180 degrees in each triangle. All right. So definitely write that down. If this is our first problem, find the sum of the interior angles of a heptagon. Well, we need to use this formula because it's the formula or the theorem for the interior angles. And then we just have to look at a heptagon. Okay. Now, here's the thing. A lot of students always say, whoa, holy cow, I forgot what a 8-sided shape is called, what a 10-sided shape is called. You are free to look those up, right? Just you can do a quick Google search, or if you want, like heptagon, how many sides are in a heptagon? That's stuff that I think it was 6th grade when you guys covered that. But if you don't know it, that means n is 7. Hepta means 7 sides. So when you have a problem like this, you have to know the formula and you have to know what that is. And if you don't know what that is, please look it up. All right, so then it's actually pretty quick. How many total interior angles are there? Well, if I have 7 sides, 7 minus 2 is 5, which tells me there's going to be 5 triangles, and 180 times 5. You would think I'd have this memorized by now, but so there are a total of 900 degrees inside of a heptagon. Now, think of all the problems I could ask you. What if I just changed the word heptagon to octagon? How many sides are in an octagon? 8. Right? Or what if I say a decagon? Deca meaning 10, so 10-sided. If I do a dodecagon, that's 12. But again, if you're stuck, you can always look it up. That's acceptable and appropriate to look up a word that you don't know. All right, what about this example? And even before I reveal it, I titled it Working Backwards. So you can probably guess what we're going to do. We're going to give you the 900, and then you have to work backwards to figure out how many sides there are. But in this case, let's look at this one, right? So what do we know? We know the sum of the measure of the interior angles of a convex polygon. And we'll talk about this convex in just a second. Don't worry about the word convex right now. But the sum is 2,700 degrees. How many sides does that polygon have? Why don't you work on this for just a minute? Here's how my brain works. I see this word right here. I see the sum, or this phrase. I see the sum of the measure of the interior angles, and I'm thinking, all right, That's this formula, right? N minus 2 times 180, and N is the number of sides. And then they tell us what that sum is equal to, 270, or excuse me, 2,700. Now I have an algebra problem, and you have a couple of options for solving this. Remember, we're going to work backwards, so we're going to find N. You have two options here. This is 180 times N minus 2. You could distribute the 180. I really hope you don't, because I hope you are trying to get N by itself. So we're just going to divide both sides by 180. And now what that gives us is basically the amount of triangles that we have left over, right? That tells me there were 15 triangles, because that's what N minus 2 was, but I don't want to know the number of triangles. I want to know the number of sides. So then the last step is moving the 2 over, and that means N is 17. So we have a 17-sided polygon. Now, sometimes people will write it like this, a 17agon. There might be an official name. I honestly, I really don't care if once you get over 12, I don't care what the name is. Even 11, we don't use that often. Um, you could look it up if you want. I I don't think we have enough time, but it's kind of a interesting piece. Okay, what about exterior angles? Okay, exterior angles, and this is just the theorem. We're not going to develop it here. We're just going to kind of give it to you. So now we're focused on the sum of all the exterior angles for any polygon is 360 degrees. It doesn't matter the amount of sides. It's just 360 degrees. I'm going to do a real quick visual that I don't want you to write down. Let's see if this works. Okay, so look at this picture that I have right here. And again, you don't have to draw this, but here's how my brain works. If I make it bigger, that doesn't, or smaller, that doesn't change the angles, right? The angles stay the same. But what if I shrink this down so small that it's really hard to see? What does it actually kind of turn into? It turns into a dot or a circle, right? And if it turns into a circle, that's not a circle. If it turns into a circle, how many degrees are in a circle? 360 degrees, right? So that's kind of the idea here, is that if I keep taking exterior angles, the angles on the outside, they will always add up to 360 degrees. So here's a problem. It's up to you if you want to actually draw the picture for it, but I'd like you to go ahead and if I give you the exterior angles, can you find the value of x that satisfies this equation? All right, so let's take a look here quick. All of these spots are exterior angles, and they're all of the exterior angles for this polygon. So if they add up, they have to add them all together. It should equal 360. And then it's just some really quick algebra. You get the value of x being 60 degrees. So there's a really quick question here. So remember, when you are adding the x's together, x plus x is always 2x. If we were multiplying x times x, that would be an x squared. But since we're adding, it's just adding the like terms together. So it's just 2x plus 140. Okay, so I'm going to give you guys a second to write this down. This is our definition of a regular polygon, and that's key, is this word regular. When you're reading math, every word is extremely important. When you see the word regular, what that means is the polygon is equilateral and equiangular. So we can add markings to this, and we can actually take the two theorems that we know, that we just learned, and we can find the measure of each interior and exterior angle just from the word regular and the number of sides. So I'll give you guys a second to get caught up here. But notice my congruent markings. Because it's equiangular or equilateral, all the sides are congruent. Because it's equiangular, that means all the interior angles are the same. So I'm going to give you a second to fill this out and see if you can answer these two questions. Given this picture, what is the measure of each one of these interior angles in a regular pentagon? And pentagon has 5 sides. And then if you get that one, see if you can figure out the measure of each exterior angle. So how do we take this whole idea that we just learned and apply it to the new concept of a regular polygon? Well, to find the measure of each interior angle of a regular polygon, or pentagon, remember a pentagon has 5 sides, I need to take the interior angle sum theorem that we just did and figure out how many angles are there. Total. What is the total sum of all these? So if I have 5 sides, that means there would be 5 minus 2 is 3 triangles, and 3 times 180, I believe, is 540. All right, so this is my total. If I have a total of 540, but each one of these angles is exactly the same, all I have to do is take the 540 and divide it by the number of sides. So 540 divided by 5 tells me each one of these angles is 108 degrees. All right, so we're using the triangle sum theorem, figure out the total, and then because they're regular, because of this word right here, and we know there's 5 sides, divide that total by 5, and that will give you each interior angle. Now you have there's a nice way to do this, and there's 2 fast ways to find the exterior angles. And let's think of this, right? If I asked you to find this interior angle right here, or excuse me, exterior angle, well, that exterior angle has to be a linear pair with the interior angle. So if you know the interior angle and you subtract that from 180, you get 72 degrees very quickly. And since all the interior angles are the same, the exterior angles are also equal in a regular pentagon. So that's one way to do it, is use the idea with linear pair, and it relies on the fact that we know the inside angle. But what if we don't know the inside angle? A faster way to do this is, because it's an exterior angle, it's 360 degrees for all of the sums of the exterior angles, and divide that by the number of sides, and you'll get the same answer we got before. So two ways to think of it. But this idea of a linear pair is really helpful moving forward. Okay, so that was section 8.1. It was all about interior angles and connecting to the amount of sides, or exterior angles and the amount of sides. What we're focusing on for basically the rest of the trimester is going to be, ooh, I want to show you one thing here quick. It's going to be quadrilaterals. So I'm going to jump back to this really quick, and I want to show you one fact that is really important to know. If I have a quadrilateral, 4 sides, the total sum is always 360 degrees, right? If I add up all of these interior angles for every 4-sided shape, it will always add up to 360 degrees. That way, you don't have to do the work. If you know it has 4 sides, you know all of the interior angles have to add up to 360. Okay, we're not going to write a ton down for this, but our focus now is 8.3, and the topic is parallelograms, specific types of 4-sided shapes. All right, now the goal today is how can I prove? And there's that word prove in geometry, which means we are going to do some 2-column proofs over the next couple days. And how do I prove that a shape actually is a parallelogram? Well, before we can prove that something is a parallelogram, we have to officially define the word parallelogram. And notice the word parallel is in it. That's the part of the definition of a parallelogram is based off of that word parallel. Okay, so we are going to go through 6 slides. That's all these ones in pink. I do not want you to write any of this down because this next slide right here is going to summarize everything. And we do not have enough time for you to write all of this down, but it will be posted on Schoology, so you can always go back and look at it if you need to. All right, so we don't need that. Okay, and let me just say this because some of you might need to hear it right now. If you have a cell phone in your hand, if you're watching TV, turn it off, right? Don't get distracted right now. Okay, just kind of hang tight and don't write any of this down. We're going to go real quick. So what is the definition of the parallelogram? Well, let's look at this kind of a different way around. If you have a quadrilateral, so you have a 4-sided shape where both pairs of opposite sides are parallel, what can we say about the quadrilateral? Well, it's a parallelogram by definition. We're officially going to define parallelogram tomorrow, but so if I know I have 4 sides and opposite sides are parallel, it's a parallelogram. Okay. The other property, property 1, is what if you have a quadrilateral where both pairs of opposite sides are congruent? What can we say about the quadrilateral then? So I know it has 4 sides, and I know that opposite sides are congruent. What conclusion can we make? All right, so again, don't write this. Let me show you with a proof. Okay, and I just want you to appreciate this and kind of see how it works. All right, so what's given? Well, right here, both pairs of opposite sides are congruent. Okay, opposite sides are congruent. That's given. So I get to put AB is congruent to CD, and AD is congruent to CB, right? That's what's given, but it's not officially given in the terms, so I need to write the definition of congruent. So AB congruent to CD, AC congruent to CB. So opposite sides are congruent. Then what we can do is see this green dotted line. It originally isn't there because they don't tell me I have a picture that looks exactly like this. It's called an auxiliary line. An auxiliary line is one that you can draw in to help you do your proof. Well, let's look at that. By drawing this dotted line, by the way, I could have drawn it this way too. It doesn't really matter. I chose A to C. We could have done B to D. But if I draw that in, that tells me I have the reflexive property. AC is congruent to CA by the reflexive property. And notice what I'm doing. I'm getting to the point where I can prove that the triangle on the bottom is congruent to the triangle on top by side, side, side. And this is our goal. We're going to take what we've already learned, proving triangles are congruent from last trimester. You need to know how to do that to be successful in this piece. Well, now, what else can I do? I can use CPCTC to say that angle DAC, this angle right here, is congruent to BCA, and that's by CPCTC. And then, what do I know? I have a Z here. Now, I might delete this just so it doesn't take up my full image, but notice, because I proved that these two blue angles are congruent, that means that this line and this line are parallel because of alternate interior angles converse. Right? If alternate interior angles are congruent, then this side here is parallel to this side here, and that's what I just proved right there. So I proved I have one pair of parallel sides. Well, wait a minute. Can't I use CPCTC again and say that the other angles, angle, no, ACD, that would be this angle down here, and CAB would be this angle here. They are parallel. So now if I do the Z going this way, those two angles are parallel, which means alternate interior angles converse proves I have another pair of parallel lines. So I'm going to go ahead and add that. Whoa. I'm going to add that to my picture. And what did I just prove now? I have two pairs of parallel lines. Well, wait a minute. Two pairs of parallel lines, or opposite sides being parallel, is the definition of a parallelogram. So I proved that ABCD is a parallelogram because I used the definition of the parallelogram. Opposite sides are parallel. Now that's a lot, right? And what did I do? I basically did three things. The red work, most of the red work, is proving the triangles are congruent. That's from chapter 4 in our book. And then I used CPCTC, which is still chapter 4. So none of this stuff is new. The only new part is the very last step. And it's just proving, in this case, it was opposite sides were parallel. Okay? Now, that's a lot, right? That would take us 10 minutes to write down, so we're not going to. But now that I proved this, I could potentially use this as a theorem. So instead of proving that opposite sides are parallel, if I know opposite sides are congruent, it's definitely a parallelogram because I just proved it. All right, property 2. What if we have a quadrilateral where both pairs of opposite angles are congruent? Okay, and again, don't write this. What can we say about the quadrilateral if opposite angles are congruent? Well, let's take a look. Now, this is a little bit different. If opposite angles are congruent, angle D and angle B, let's both call those X. And angle C and A are congruent, so let's call those Y. Well, what do we know? Well, wait a minute, these are interior angles. Interior angles for any quadrilateral have to add up to 360. So if I add the X's together and I add the Y's together, 2X plus 2Y has to equal 360. What if I divide both sides by 2? What did I just kind of show or prove? I just showed that x plus y. Now look at where x is. X plus y equals 180. Wait a minute, aren't those consecutive interior angles? If consecutive interior angles are supplementary, that means that opposite sides are parallel. Wait a minute. Isn't this x plus this y also consecutive interior angles, and they add up to 180? We algebraically kind of showed that. So now opposite sides are parallel. So here's another property. If you know that opposite angles are congruent, then our shape is a parallelogram, okay? So my conclusion is ABCD is and instead of writing the word parallelograms, we just kind of draw one. Hopefully it's a little neater. So there's my conclusion. Okay. All right, next one. What if in a quadrilateral, you know that consecutive angles are supplementary? Wait a minute. Isn't that what we just proved? If you know for sure that consecutive angles are supplementary, so if angle B and angle C, you can clearly see they're not the same, but if it's given, which by the way, this is kind of like our given information, that means that opposite sides are parallel. And these are consecutive angles, so if they're supplementary, that means these two sides are also. So here, again, we proved that ABCD is a parallelogram. And it's all based off of the information that we've mastered, hopefully, from trimester 1. All right, so what, and this is a very interesting one, what if you have a quadrilateral where the diagonals bisect each other? Ooh, interesting. Okay, so here I have a four-sided shape, and now the diagonals bisect. And this is kind of important. The way we would write this is if AC bisects BD. Now this comes up on the can figure it proofs, and a lot of students make mistakes here. If AC bisects BD, that means that the line AC is cutting BD into two pieces. So if I'm using this statement, AC cuts BD into two equal pieces. Now, what if it's written the other way around? Because diagonals bisect each other. So what if I say BD bisects AC? Okay, now BD is cutting AC into two equal pieces. Well, look at what that did. The diagonals actually have two congruent sides. And if I use vertical angles, now all of a sudden, and I'm not going to do a full proof. I'm going to show but not prove that this is a parallelogram. But I could prove that the top triangle up here, triangle 1 is congruent to triangle 2. And if they're congruent, then that means that you could either show an angle here, or I could show that this side up top is congruent to this side on bottom. And then if I do the other vertical angles on this side, that shows the left and right triangles are congruent by side, angle, side. The top triangles are congruent by side, angle, side as well. Then all of a sudden I could use CP/CTC and prove that opposite sides are congruent. And if opposite sides are congruent, wasn't that just the property we had right here? If both pairs of opposite sides are congruent, then our conclusion was ABCD is a parallelogram. So I didn't show this, but we just proved because opposite sides are congruent. Now you could have also used CP/CTC and have done some alternate interior angles and proved opposite sides were parallel. So you could have used the definition to prove they're parallel. All right, last one. I know this is a lot and you might feel overwhelmed. Don't be. I'll show you. It's actually going to be friendlier than it looks today. Okay, if you have a quadrilateral where one pair of sides is parallel and congruent, okay? Now this should say exactly one pair. What do we know? Well, let's look at this. Okay, we're not going to fully set this one up either. So one pair of sides is parallel and congruent. Let's pick. Let's say that this side is congruent to this side, and then it has to be parallel as well. So one pair of side is both parallel and congruent. So this side and this side. I can't have this side parallel and this side congruent. They both have to be parallel and congruent. Well, I'm not going to go through a full proof here. We don't have time. So let's just look at what we know. Okay? Using the auxiliary line, can I prove that these two triangles are congruent? Well, I already have one pair of sides, and I have the reflexive property. And then if I use the z, I can say, because of alternate interior angles, that angle CAB is congruent to DCA by alternate interior angles. Well, now, side angle side, side angle side proves that these two triangles are congruent, which means CPCTC will show us that opposite sides are also congruent. So because opposite sides are congruent, it's a parallelogram. Or we could prove that this angle right here, and by the way, there are many ways to do these proofs. I want you to be aware of that. But I could prove that this angle and this angle are congruent by CPCTC, and then that would give me alternate interior angles, which would prove that this side is parallel to this side. And then I would have enough to show that opposite sides are parallel, so I could use the definition of the parallelogram as well. Okay, but notice we did the same step. I didn't write this out, but when you're doing proofs, you want to prove the triangles are congruent, you want to use CPCTC, and then you want to use that new information to prove that a parallelogram is, that it is a parallelogram. Okay, so we just wrote down, or we just covered a lot. Here's what we covered, okay? So I would like you to write this down. If you have a four-sided shape, look at how all of this is stated. So we've got 1, 2, 3, 4, 5 properties. If both pairs of opposite sides are congruent, then it's a parallelogram. If both pairs of opposite angles are congruent, then the four-sided shape is a parallelogram. If consecutive angles are supplementary, then it's a parallelogram. If the diagonals bisect, then it's a parallelogram. Or if you have one pair of sides that is both parallel and congruent, then it is a parallelogram. Okay, let me show you your homework really quick, just so you're aware. Here's the homework. It's due this afternoon, and there are two parts. 8.1 is all about interior angles and exterior angles. 8.3 is about quadrilaterals being parallelograms. So notice here just quick, like in 8.1, you might have to look up what a nonagon is, okay? But we've done problems like this. In number 12, don't forget about if you see the 90-degree angle box, right? That means 90 degrees. That is an angle. Even though it doesn't have a number, we know what that is. But I want to show you 8.3 quick. And this is what 8.3 is. And let's just look at like these problems here. So it says, what theorem? Now, I don't care about the theorem number, right? If you're to look in your book, they have like 8.1, 8.2. I want you to describe what is true here that shows that this is a parallelogram. So which property is present in this picture here? And then you would confirm that, oh yeah, because this is true, it's a parallelogram. And what property is present here? What property is present here? So you're just basically saying of those 5 items, which one is true. For number 8, you're going to use one of the properties to find the value of x to make that makes this a parallelogram. So you're basically kind of doing the same thing you do in 4, 5, and 6, but then you're saying, okay, because this is true, then I can do this type of algebra problem to find x. All right, and here's the part that we are going to actually have you do. You have to prove that these two, 15 and 16, are parallelograms. And I'll just let you know, there's more than one way to do it. If you see one way and your friend finds another way, that's fine. Or if the answer I post is different than what you do, it's not technically wrong. All right, so we're just using the properties today, and we only have two proofs. These have to be written out, and you need to make sure you add your picture. Let me just basically show you this. Your proof should look like this. Now, it might not be as long, but you should have the picture, it should be interacted with, and you should have statements and reasons and a full conclusion. Okay? And then I will be posting, here are the answers. I'm going to be posting these answers. Now, I will say we reduced this assignment from years past. So I'm going to post these answers along with my proofs for 15 and 16. But when I post these answers, please know that there's more answers on there than you were assigned. Okay? All right, that's all I have. We ended a minute early. Yay. Have a good one. I'll be available from 1 to 2 in my office hours today if you need help or you have any questions.